Okay, so I am very glad to introduce Ina Entova Aizenbud from Ben Gurion University of the Negev in Beersheba and announce your talk on McKay trees. Please.
Thank you very much. So thank you very much for the invitation. It's a pleasure to be at this seminar. And I'm going to talk about joint work with Avraham Aizenbud about something which is called McKay graphs and specifically McKay trees, which are named after John McKay, who sadly passed away very recently. So I will start by introducing what are McKay graphs. Let me know if there's a problem with the sound. So I will be working over the base field of complex numbers. And what is a McKay graph? So you're given a finite group G and a finite dimensional representation rho. I will always work in the setting of finite dimensional representations. We can define the McKay graph as a directed graph whose vertices are irreducible representations, and we draw an edge between two representations, lambda and mu, if lambda times rho contains mu as a direct summand, and the multiplicity of this direct summand mu is the number of edges we draw between lambda and mu. So I will soon speak about the reason for defining these graphs, but I will start with some examples. So the first example would be just to take a cyclic group and a one-dimensional representation of the cyclic group. So in that case, we can draw the McKay graph, and you can see that this is actually a cycle because we just go over all our irreducible representations, and of course the multiplicities are all one. So this is the first example of how McKay graphs can look like. And here are some conventions. When we draw a vertex, we'll always label it with its dimension, the dimension of the corresponding irreducible representation. And the vertex corresponding to the trivial representation will label it by star, because actually it is sometimes important to know which vertex corresponds to the trivial representation. And also, just to save some writing, we will draw one single undirected edge for every pair of edges in opposite directions. So we already saw an example of a McKay graph, which is a cycle, but in fact, we can also get a disjoint union of cycles of same size from the same idea. We take a product of two groups, one of them being cyclic, and we take a representation which is irreducible, which is an irreducible representation of the first component and the trivial representation of the second component. So in this case, I took the product of the cyclic group on 8 elements with the cyclic group on 2 elements, and the cyclic group on 2 elements gave me precisely 2 components. And in general, it is really natural to expect to obtain the graphs which are disjoint unions of directed cycles, because this is exactly what happens whenever we take our representation rho to be of dimension 1. So here are some more examples. If we take the 2-dimensional representation of the cyclic group, which is the direct sum of an irreducible representation with its dual, then what happens is that our McKay graph will be a union of 2 graphs, which are basically put one on top of the other. We identify the vertices for 2 directed cycles, and we get one edge in each direction between 2 adjacent vertices. So this is just replaced by an undirected edge. This way we can get an undirected cycle, and again we can use this to construct graphs which are disjoint unions of undirected cycles. But here is an example which is actually not a cycle. if we take the dihedral group D4, the symmetries of the square, and we take its natural two-dimensional presentation, the graph which we get is a star graph, right? So this is actually a very nice example. And again, as you can see, we have undirected edges which correspond to the fact that we actually have an arrow in each direction whenever an undirected edge is drawn. Now, one can ask, well, can we recover the group and the representation based on the McKay graph? And it is not particularly surprising that this is not the case, because the McKay graph contains only information which can be accessed from the character table of the group. And we know that there are groups with the same character tables. So for instance, the dihedral group and the quaternionic group have the same character tables. And so it is not very surprising that we will get the same McKay graphs when we take the corresponding two-dimensional presentation of the quaternion group. Let us see some more examples. So if we take the symmetric group S3, we can draw the graph for the reflection representation. And here you can see for the first time that our graphs can actually have loops, right? Loops just meaning that when we tensor a certain representation with the reflection representation, we get the same representation as a direct summand. And of course, in this case, this vertex labeled by 2 corresponds precisely to the reflection representation itself. And here is an example where we actually take a reducible representation. If we take an elementary 2 group, so this is just the cyclic group on 2 elements to the power n, we can take a very big representation, which is just a sum of sign representations for different factors. And in that case, the graph which we obtain is actually an n-dimensional cube. And there was an idea due to I think Georgia Bankard and her co-authors that one can study walks on different graphs, for instance, on cubes, by applying some ideas from the theory of McKay graphs.
So Ina, so far it was all multiplicity 1, the graph? I mean, the edges were...
Yes, so far it has always been multiplicity 1. So here is a graph where the multiplicity is, not all the multiplicities are 1. If we take the symmetric group and again we take the reflection representation, we'll get a pretty complicated graph. It still looks decent, but I have to say that in general, if you consider McKay graphs for irreducible representations of symmetric groups, they do not look nice. So here you can see that even for S6, the graph is already pretty complicated. It has quite a lot of loops. And in the middle, you can actually see a double loop. So the multiplicities are not 1 anymore. And of course, the fact that here it is actually symmetric is due to the existence of the sign representation. So the fact that we can tensor with the sign representation means that we have a certain symmetry of the graph. And more generally, whenever we have a McKay graph and a one-dimensional representation of our group, this actually gives us a symmetry of the McKay graph. So the group characters of the group G act on the McKay graph. And here is one more example of a graph which is not simply laced, so the multiplicities are not 1. If we take the Aizenbud group for the field F5, then we can consider the irreducible representations. There will be 4 irreducible representations of dimension 5 and 25 irreducible representations of dimension 1. So they are drawn in this picture where the multiple dots actually stand for the remaining one-dimensional representations. And so if we choose one of those irreducible 5-dimensional presentations, the graph which we'll get is sort of blown up square. So as you can see, it is both directed and it has a lot of multiplicities because the bold edges actually stand for 5 edges each. So a little bit about where these graphs come from. So the reason McKay was studying them is because there is a very beautiful correspondence, which I believe is due to McKay himself, but of course based on a lot of previous works on related subjects. Namely, if we consider finite subgroups of SU2 together with the natural 2-dimensional complex representation of these finite subgroups, we can draw the corresponding McKay graphs, and these McKay graphs turn out to be precisely the affine Dynkin diagrams, which are simply laced. So what does it mean, affine Dynkin diagrams? We take the usual simply laced Dynkin diagrams of types ADE, and we add one more vertex, which is precisely the star vertex, which we draw here. So this actually allows to classify the finite dimensional subgroups of SU2 in one more way. And the fact that we get those affine Dynkin diagrams as McKay graphs is actually not just a coincidence, because this is part of the correspondence between finite subgroups of SU2 and singularities of the quotients of the complex plane C2 by those finite subgroups, and of course the corresponding simple Lie algebras. So I will not get into this correspondence, but I just want to go quickly over the corresponding finite subgroups of SU2. So let me go back to the previous slide for a moment. If I take the first finite subgroup, which corresponds to the affine Dynkin diagram of type AN, that would be the cyclic group on n+1 elements. The finite subgroup corresponding to the affine Dynkin diagram of type Dn is the binary dihedral group. So what do I mean by binary? I mean a central extension of the usual dihedral group by a center of order 2. So where does this central extension come from? Well, we have, of course, our two covering morphism from SU2 to SO3. And so the dihedral group can be seen as a subgroup of SO3. When you pull it back to a subgroup of SU2, you get precisely the binary dihedral group. And similarly, if you consider the symmetries of the regular tetrahedron, octahedron, and icosahedron, you get subgroups of SO3, which when pulled back to SU2 will give you binary tetrahedral subgroup, binary octahedral subgroup, and binary icosahedral subgroup. And again, these are just central extensions of the classical tetrahedral, octahedral, icosahedral subgroups by a central subgroup of order 2. Any questions?
May I ask a question, please?
Yes. Yes.
Yes. Are those numbers the weights of, if you consider the highest root of the corresponding Lie algebra?
Yes.
Those are the multiplicities, the dimensions of the. Okay. Yeah. Yes. Is there something smart to say about that?
There are many smart things to say about that, but basically the idea is that these numbers, right now we describe them as dimensions of some irreducible representations, but we'll see in a few slides that they're actually intrinsic to the graph. So if I have a graph, I can actually find, if I have a graph which is secretly a McKay graph for some group and some representation, I can find these I can determine these numbers uniquely from the shape of the graph itself. And because this is the case, it is not so surprising that when we study the same graphs in different settings like quivers or Lie algebras, then these multiplicities occur again.
Okay, thanks.
Yes. Okay, then I will continue. So what we wanted to study in our work was actually what could be the possible shapes of McKay graphs, because we already saw that one can easily get unions of cycles, directed or undirected. And in fact, one can easily say that something about getting complete graphs. Namely, we can get a McKay graph, which is a complete graph, if we take, for instance, the group to be the cyclic group, and we take a pretty big representation of dimension n-1. We just take the shift representation on Cn of the cyclic group, and then we quotient out by the subspace of constant coefficients. So this will give us a complete graph on n vertices. And so one cannot say, well, okay, if we have a McKay graph for some irreducible representation, we can always build out of the McKay graphs for irreducible representations, McKay graphs for reducible representations, just by taking the graph for each of the irreducible summands of our representation, and then gluing them on top of one another. So for instance, this complete graph is actually glued out of many, many cycles. But the more interesting question is, can we study complete graphs? Can we get a complete graph when we actually consider an irreducible representation of some group? And this question is easy to answer, because if we have an irreducible representation of a group, then the corresponding McKay graph will always have the vertex, which is labeled by star, which corresponds to a trivial representation, which will only be connected to rho. So it will never be a complete graph. So what we are going to discuss today is actually the opposite question. So we saw that complete graphs are not that interesting. We can get them, but not as sort of irreducible McKay graphs in a sense. But can we get, on the contrary, McKay graphs with very few edges? So McKay graphs with very few edges would be trees or unions of trees, namely forests. And it turns out that one can actually classify all McKay graphs, which are trees. So here is the main theorem. If we have a finite group and a complex representation, so that the corresponding McKay graph is a tree, then we can immediately say the following. First of all, this representation rho will be irreducible and self-dual. This is actually not that difficult. But furthermore, we can actually say what are the possibilities for G and rho. Namely, G can be one of the following. G can be a dihedral group of order divisible by 4. In that case, rho would be just the natural two-dimensional representation coming from the real representation. G can be a finite subgroup of SU2 of types D or E, as in the list which we saw before. Or G can be something funny, which is called an extraspecial group of order 2 to some odd power. And I will soon explain who are those extraspecial groups. In that case, G has a unique irreducible representation of dimension greater than 1. This representation has dimension 2 to the n, and rho must be this 2 to the n dimensional representation. And the shape of gamma in that case is one of the following. If we are dealing with G, which is either a dihedral group or a binary polyhedral group of type D, then our graph will be an affine thinking diagram of type Dn. If we are dealing with a binary polyhedral group of type E, then our McKay graph will be an affine thinking diagram of type En. And if you are dealing with this case of an extraspecial group, we'll actually get a graph which is a hedgehog. It has a lot of leaves and just one vertex which is connected to all of them.
So by the way, the tree you mean with multiplicity 1, the edges?
Yes, so I mean multiplicity 1, but this is an undirected tree. Yeah, I see it's actually not written here. So it is an undirected tree. I have the multiplicities are 1, but every edge comes with an edge in the opposite direction.
You mean you don't care about the rotation? That's what you mean, right?
I don't, and I require that my tree does not have unoriented edges, in the sense that whenever I have an edge from lambda to mu, there must be exactly one edge from mu to lambda. So basically, my gamma should be a tree in the sense of simple undirected graphs. Okay, so who are the extraspecial groups? So the extraspecial groups are P groups, which are built in the following way. We can take an elementary abelian P group. So this is just the cyclic group on P letters to some power, or if you want a vector space over Fp. And then we take a central extension by the cyclic group Z modulo Pz. And these groups have been studied by Aschbacher, Isaacs, Diaconis, and others. And it turns out that there are actually not so many of those. Namely, we can say the following. First of all, every such extraspecial P group has order P to some odd integer. And in general, for every size we fix, so for every P and every power P to the 1 plus 2n, there are exactly 2 non-isomorphic extraspecial P groups whenever n is greater or equal than 1. So what are the examples of these groups? Well, first of all, we have, of course, the cyclic group on P letters itself. This is what we get for n equals 0. For n equals 2, we get something a bit bigger. Namely, we get so for n equals 1, what we get is exactly so one of the 2 groups which we get is exactly the Heisenberg group for P. So this is the Heisenberg group over Fp. And in general, if I take the Heisenberg group corresponding to the finite vector space Fp to the n, this will always give me an extraspecial P group. And there is another extraspecial P group, which is a bit more similar to the quaternion group. So for P equals 2, the 2 extraspecial groups of order 8 are exactly the dihedral group, which is the Heisenberg group for F2, and the quaternionic group. And in fact, all the extraspecial 2 groups of higher orders can be obtained from central products of several copies of the extraspecial P groups of order P to the third. And in the case when P equals 2, which is the case which we are interested in, this means that every extraspecial 2 group which has order greater than 2 will be a central product of several copies of the dihedral group D4 and 1 or 0 copies of Q8 of the quaternion group. So let me give an example. When we consider the extraspecial 2 group of order 1 plus 2n, and we ask what would be the irreducible representations, then we get 2 to the 2n one-dimensional representations, which actually come from the quotient of our group by its center. So the quotient of the group by its center is an elementary 2 group. And so we get a lot of one-dimensional representations. And there is one other representation which has dimension 2 to the n. One other irreducible representation. And for this representation, the graph gamma G rho, the McKay graph, would be exactly a hedgehog, so a star graph, which has 4 to the n spines. So for instance, for n equals 2, we'll get 16 leaves, 16 spines, and 1 vertex in the middle, which is labeled by 4, which is 2 to the 2. So these are the types of trees which we can get except for the affine linking diagrams of types D and D. So now let me tell you a little bit about the ideas behind the proofs, and in general what is known about McKay graphs. So first of all, when we consider a McKay graph, it is natural to ask what does the adjacency matrix look like? And the adjacency matrix can be labeled by the columns and the rows of the adjacency matrix can be labeled just by irreducible representations of gamma, of course. And as we know, the number of edges between 2 vertices lambda and mu would be the multiplicity of mu in lambda times O. So the first useful statement is that the multiset of eigenvalues of this adjacency matrix is actually the multiset of values that the character of rho takes when we consider its values on conjugacy classes of G. And the corresponding eigenvector for the eigenvalue psi rho would be the function which sends each irreducible representation to the value of its character on the given conjugacy class. So this is already something which connects to what Roberto was asking earlier. The information about these eigenvalues would be stored inside the adjacency matrix of the graph. So if we see a graph and we know it is a McKay graph, we can immediately recover all those eigenvectors and eigenvalues. And in particular, if we consider the eigenvalue with the maximum absolute value, well, we have one which is obtained when we plug in the unit of our group instead of G. And in that case, the eigenvalue is just the dimension of rho. The corresponding eigenvectors would be just the dimensions of the corresponding irreducible representations. So this is exactly the labeling of the vertices which we saw earlier. So the labeling of the vertices can be determined from the adjacency matrix of the graph. So here are some more statements. All of these are due, I believe, to McKay, maybe earlier. So the next statement is is about connectivity. So when can we say that our graph is connected? This happens if and only if the representation rho which we are dealing with is faithful. And in that case, we actually know that the spectral radius, the maximal eigenvalue which we can get, has multiplicity 1. So there is a unique eigenvector which we can find, which corresponds to the spectral radius. And of course, this eigenvector will have non-negative integer, so a positive integer enters. What about the question of when the graph is undirected? Well, the idea of reversing all the arrows corresponds actually to taking the dual to the representation rho. So if we take the graph corresponding to the dual representation, this is obtained from the graph of rho by reversing all the arrows. And of course, this means that our graph is undirected precisely when rho is self-dual. And furthermore, one can actually say something about the meaning of being a loopless graph. Namely, if we start with an irreducible representation rho, then we have no loops if the center acts non-trivially on the representation. This is not an if and only if statement, just one direction. And the last thing which it makes sense to mention is what happens when we want to consider bipartite graphs, because after all, the trees which we are considering are of course bipartite. And so in this case, we have the following statement. If our representation rho is irreducible and faithful and self-dual, so that means in particular that the graph is undirected and connected, then we can say that the graph is bipartite if and only if the center of the group is just a cyclic group on two elements. So these statements already tell us that if we are studying McKay graphs in shapes of trees, we can say some things. We can say that the representation which corresponds to this graph is faithful and self-dual. And if we manage to prove that our representation is also irreducible, then we can immediately say that the center of our group is actually of order 2. So here is a slightly more detailed classification of McKay graphs with spectral radius 2. So these are precisely the graphs corresponding to representations of dimension 2. And here I am assuming that my graph is undirected and connected, which means that rho is self-dual and faithful. So in that case, we can actually say that something about G and about rho. So either G would be a subgroup of SU2 and rho the corresponding two-dimensional representation, or G would be the dihedral group and rho would be the corresponding two-dimensional representation coming from the real plane. And as you can see, when we take the dihedral group of order divisible by 4, we will get a McKay graph, which is actually a tree which is just the affine diagram of type D, affine linking diagram of type D. But if we take a dihedral group whose order is not divisible by 4, we'll get something with a loop at the end. So it's like the affine linking diagram, but with the last two leaves sort of glued together. Okay, so here is the key formula which we use to prove our statement. So if we start with an undirected McKay graph, and we want to compute the number of circuits of length k in our graph. So when I say circuit, I just mean a walk, which could include possible repetitions. And of length k means that I traveled through k edges, and I also want these to be closed circuits. Yes, my walk begins at n and ends at the same vertex. So the number of closed circuits of length k in my graph would be exactly the trace of the kth power of the adjacency matrix. This is a general statement about graphs. Yes, so the diagonal entries in the kth power of the adjacency matrix are precisely the number of circuits of length k which begin and end at a certain vertex. And if I want to sum over all the possible vertices, I will get the trace. And since we know that the adjacency matrix is diagonalizable, this immediately means that the number of circuits is actually the sum over all the conjugacy classes of the kth powers of the values of the character of rho. Now, if we take k equals 2, I'm interested in circuits of length 2. So that means that I leave my vertex and I immediately come back. This actually means that I'm computing twice the number of edges in my graph. And so we get from the formula above that twice the number of edges in our graph is the sum of squares of the values of the character of rho on conjugacy classes. And if we work a little bit more, we can actually prove that this is equal to the sum of the dimensions of the endomorphism space, the restriction of rho to the centralizer of a representative of the conjugacy class. So this is the formula which you see right here. So why is this useful? We can immediately get the following corollary. If we take the equality above and we divide both sides by the number of irreducible representations of G, which is the same as the number of conjugacy classes in G, then we see that 2 times the ratio of edges in our graph to the number of vertices in our graph is the average of the dimension of this endomorphism space, which means the following. So if we have a graph which has very few edges, connected but very few edges, then left-hand side is pretty small. And in particular, this means that the average size of the right-hand side of the dimensions of endomorphisms in the right-hand side is also small. So this means that when rho is restricted to the centralizer of an element X, it tends to have very small length, which brings us closer to proving that in our case, rho will actually be irreducible. Any questions? Okay, so now let us go back to the main statement. We want to prove that given a graph, a McKay graph, which is a tree, undirected, as I said, we want to show that rho is an irreducible self-dual representation. The part about self-duality, we already saw it due to the fact that our graph is undirected. And we also want to say that we can actually classify G and rho. So here is a sketch of proof. If we consider the number of edges in our McKay graph, this is exactly the number of vertices minus 1. So this means that the ratio edges to vertices is smaller than 1, and twice this ratio, which is exactly the average the average dimension of the endomorphism space of this restriction is also smaller than 2. So since the dimensions are integers, we can immediately conclude that there is at least one X for which the dimension of this endomorphism space is 1. In particular, that means that the restriction of rho to this centralizer subgroup CX must be irreducible, and so rho was irreducible to begin with. In fact, we can say the following thing. Rho is restricted to an irreducible representation precisely when X is a central element. Of course, if X is central, then the centralizer of X is just the entire group. So if rho was irreducible, there is nothing to be said. But we can also say another thing, namely, if we consider such a restriction to a centralizer, and this restriction is irreducible, then X acts on our representation by an operator which commutes with all the elements from the centralizer. So it acts by a scalar. And if it acts by a scalar, it means that it must be in the center of G, because the representation is faithful. So what do we do with that? Well, now we use our formula, our key formula again, but we compute things with a little more care. Namely, we said that whenever X is not a central element, the restriction of rho to the centralizer of X will not be irreducible. So the dimension of the corresponding endomorphism space will be at least 2. And if we consider the sum of such dimensions, but when we run over all the X's which are representatives of conjugacy classes and not central, we will actually get at least 2 times the number of irreducible representations minus 2. So our key formula tells us that this inequality must be an equality, which means that whenever we consider this endomorphism space of the restriction, its dimension is always 2 whenever X is not central. So now we have 2 options. The first option is, the first possibility is that the centralizer is abelian for some element in G. If the centralizer is abelian, then we know that all the reducible representations of this centralizer are 1-dimensional, and having the endomorphism space of the restriction of rho, which is 2-dimensional, we can immediately conclude that rho is just a sum of 2 irreducible representations, non-isomorphic. The case when Cx is not abelian for every X is actually trickier. And in that case, we obtain that G is the extraspecial 2 group, and rho is its unique irreducible representation of dimension greater than 1. So this is the end of the sketch of the proof. And now, one last remark. What happens when we consider forests? So what happens if when our graph is a union of trees, but these trees, but not necessarily just one tree? So in that case, we can still say that our representation is irreducible and self-dual. This is actually not very difficult. It is not faithful anymore if the graph is not connected. This is something we saw. But we can say something about G modulo the kernel of this representation. Namely, I apologize, I see here that I wrote N n instead of the kernel. So namely, if we consider the connected component which contains a trivial representation marked by star, the vertex marked by star, this component must be isomorphic to the McKay graph for G modulo the kernel with the representation rho. Rho, of course, factors through G modulo the kernel. So rho is actually a representation of this quotient. And so this immediately means that we can use our previous classification to say that at least the connected component containing star can be described by the shapes which we list in the main theorem. And in particular, the group G modulo kernel is also one of the groups listed in the main theorem, and rho would be the corresponding representation of this quotient. Now, can we classify all the possible G's in this case? Well, the answer is not in a very nice way, in the sense that if we take G to be a product of one of the groups listed in the main theorem with any other group, and we take an irreducible representation, which on the first factor is one of the rows listed in the main theorem, and on the second factor is trivial, we'll just get a union of several copies of the trees which we saw in the main theorem. So, of course, this means that this way we can actually build plenty of forests for G's of arbitrary sizes, right? Just by taking one of the groups which we know and taking the product with any other group at all. But a conjecture which we have is actually that this is the only picture which we can get, namely that the components of the McKay graph, which is a forest, must all be isomorphic to each other. So we cannot get different components which are non-isomorphic trees. And this is something which we can actually prove whenever G modulo kernel is an extraspecial to group. And we are still working on this in the case when this quotient is a dihedral group or a binary polyhedral group. So here is a partial bibliography about McKay graphs. So the original papers due to McKay are from the 80s, and there is a paper due to Steinberg about the same topic. And recently there have been some papers due to Liebig, Shalev, and Tiep, which actually study diameters of McKay graphs. So this is all. Thank you very much.
Questions, please.
So maybe you could say again, what was your motivation to study this question?
Well, I'm not sure I have a good answer for this, but the idea was that it looked as if this is actually a question which might have a nice answer. In general, studying the shapes of McKay graphs sounds like a completely wild problem, so we do not expect any good answer for this. But the fact that one can actually classify all the trees is somewhat surprising, because when you study McKay graphs, you usually don't use properly the shapes of the graphs. You don't really consider them as graphs, right? Because they are just, sort of partial storage of partial information about the character table. And so the fact that being a tree is actually some nice property was probably the best motivation for this. So I hope this is at least somewhat of an answer.
But I mean, these extra special groups. I mean, the Dinking diagrams, of course, they come up all over the place, obviously. But these extra special groups, I mean,
I do not know why they came up. So actually, when we started doing this, we were sure that we'll only, at least I was sure, we'll only get the Dinking diagrams. And it was surprising but nice to know that the extra special groups appeared. Because as I said, in general, if you take some finite group, you don't usually expect to get a nice McKay graph. So the fact that you get nice McKay graphs for extra special groups, for instance, for the Aizenbud groups, is for me surprising in itself. Yes, because for instance, for the symmetric groups, you usually get something horrible.
I mean, you're not aware of any geometric counterpart or any other occurrence of this extra special group? I don't know, in some other context?
No, so I only know this that they are generalizations of the Aizenbud groups, but I really don't know why would they why would the McKay graphs be nice or special. So I know that recently people had some. There were some works about representations of quivers which are McKay graphs in themselves, but I do not know any details. I just heard that there was such a thing, and I think it is pretty interesting, but I cannot say anything more detailed about this.
Okay. Any further question? If not, then yeah, yes, please.
Yeah, it may be a silly question. I'm checking now like the basic properties of McKay graphs again. I'm wondering if your classification of the trees allows you to say something else about that group whose McKay graph is not a tree. Beyond that, what was known, I see here these loopless graphs, no? Like the center acts non-trivially on row, then this McKay graph has no loops. I wonder if you've used it in both directions somehow.
And no, I didn't use it in both directions, but once you, so no, actually, I believe we didn't use it at all. Yeah, I believe we did not use it at all because here one could say, so yeah, when we are talking about trees, the representation is faithful. So it immediately means that your center acts non-trivially. Yes. So for trees, this is actually not that useful. And for forests, of course, you also don't need it because you assume that you're already working with forest. In general, it is nice. It is nice, a nice thing to use because, well, because it actually allows you sometimes to understand whether you need to factor by the center or not when you're studying a McKay graph. But yeah, it's I don't think that we have a good so I mean since we have the classification of what groups can occur when we are considering McKay graphs which are trees, of course you can say that whenever a group and the representation give us a McKay graph which is not a tree, it just means that it is not one of these pairs. But I don't think I have a very smart thing to say about this classification. Well, apart from the fact that the dimension of rho is either 2 or a power of 2. Yes. So if the dimension of rho is not a power of 2, namely the spectral radius of your graph is not a power of 2, that immediately means that it is not that it cannot be a tree if it is a McKay graph.
Okay, thanks.
Okay, any more questions? Let us thank Ina again. So our next talk is in 2 weeks, and the speaker is Raf Klackers.
So thank you very much for the invitation.